Hey, this is Joe Burnett. There's a couple of blueprints that have been floating around in the runner space that describe some pretty large architectural changes. And I wanted to take a few minutes to explain how I see them relating to each other and what they are. I'm not going to show you the blueprints and walk through each one. I'm not going to show you the code because that's just way too much. It gets into too many details, but I do want to give a high level description about how the runner works today in the aspects that are addressed by these blueprints, what each one of them is doing to change it, and the parts that overlap and the parts that are separate. So the first blueprint is one called Taskonaut by Aaron. I'll provide links to these in the description of this video. The other is steps. There's a new blueprint from Camille about steps, and I'll explain what that is in a minute. I also want to tell you about what I've been calling executor reduction. So like there's a lot of executors, and I want to address some of the orthogonal aspects that are incorporated in them. And finally, I want to talk about events. So CI events and CI steps have been like sharing a similar space of discussion, but they're not the same thing. And I wanted to show how they overlap. So let me tell you a little bit about how the runner works today. So today, runner connects to GitLab. And what it does is it receives a build. It actually gets a job in a job response, and it produces this structure called a build, which is a very rich, complex data structure with a lot of code attached to it that describes like everything about like how this specific job is meant to be executed. Like, if it's Kubernetes, like all the containers and the various features, if it's going to be in shell, which shell is it, and all the various things that you might have, like how do you want to manage the cache, etc. And what runner does is it actually uses based on executor. So there's this executor discriminator. It uses the provider, which gives a concrete environment. So it creates an executor, which comes back here. And this is all in runner's like memory space. Sometimes the executor provider does create an executor like pointing to an environment outside the runner, like in an auto-scaled scenario. But for the most part, like this is what's happening inside runner here. And so then you get the build and you combine it with the executor. And now you have something concrete that you can actually run. Like it's like what to do. You have an environment, and then runner goes through steps of, prepare, run multiple things, and clean up. And it calls these as methods on this build. And what under the hood, what happens when you do each one of these is it takes the description of what's supposed to happen, which includes, the actual script the user's provided, plus a lot of job control logic about like testing the environment, producing errors, uploading cache, just like all these various things. And it actually like uses what's called the abstract shell. And this abstract shell, it's a library inside of runner, and it produces like a shell script. So you get like the core of what the user asked for or the thing we're trying to do, and then a bunch of like code before and after to execute that. And this all gets packaged up and it gets injected into that executor. So the way that it gets injected is through SSH, and it runs this shell command over SSH, or exec in the case of Docker, Kubernetes, etc. Is it actually like uses whoever talks to whoever's managing that container and says, hey, please run this command inside this container. So that's how the code actually gets in there. So there's a couple aspects. There's scaling, there's isolation, there's job injection, and job execution. And here, a lot of that is sort of coupled into the executor and this shell script that's being produced. So there's some problem with that. Actually, one more thing I wanted to mention is actually what comes out of this is a bunch of job logs. And these job logs, we have to parse them. And we get the actual logs, and we get control codes like exit codes from Kubernetes from the logs. So there's actually quite a bit of complexity in the job logs themselves. And they're just straight up logs, just like text logs. So this has a couple problems. And I'm going deep on this because each one of these blueprints is meant to address some of these problems. And that's the overlap that I want to show. So some of the problems are that compiling each one of these scripts, it's environment specific. So if you're compiling to run on a Windows machine, you can have to use PowerShell, Linux, Bash, maybe something else, etc. The way that it gets injected in there, the way that the job control is compiled into that shell script is going to be environment specific. And that's the other problem is like all that control logic is getting compiled over and over again as shell logic. So there's like a bunch of things that can go wrong in runtime. And it's very text oriented, makes it very brittle. Also, injection is stateful. So it's just executing a command and looking at the output. So there's a lot of there's a lot of working around to be able to like reattach for example, in Kubernetes, if you lose that stream of logs, because the output from that command, that specific command, is everything, right? That's the whole, everything that you get from, to know what to do next, to send the logs, etc. Also, these executors are encompassing all of these aspects. So there's one specific keyword that addresses, scaling, isolation, job injection or the delivery of the job, and job execution. I've talked about this a little bit before about how we want to try to break it up, and we've actually been making a lot of progress in this space, and I'll tell you a little bit more about that in a few minutes. Another problem that is here is there's hard-coded steps. So there's things like pull the script, pull down the cache, the artifacts, push the cache, clean up. These are all specific steps that actually run every time, and are just sort of assumed to be part of setting up the environment. But depending on what you want to do with a job, it may not be necessary to do those. And last, I mentioned this already, but job log parsing is complex, right, and overloaded in its role. So the idea behind Taskonaut is a lot of the Taskonaut design takes these different roles and puts them behind an interface. So, for example, job execution is done by an agent that runs in the environment. And connection to that is over gRPC. So it gives you a way to multiplex different things like, execute this job, give me the logs, stop the job. Those are just gRPC calls. So putting things behind an interface is part of what we've been doing. The fleeting work that we've been doing, same thing, putting a lot of these aspects behind an interface. So the scaling goes behind the fleeting interface. VM isolation goes behind the nesting interface, etc. The way that the thing that Taskonaut does to take this a step further is it takes it it has GitLab producing a low level list of steps to run. And so does the steps blueprint. That's one of the things that they have in common is instead of sort of having this complex combination and compilation step inside the runner, let's just assume that we get at some point just a list of things to do step by step, very, very concrete, no need for interpretation, and that agent inside the environment can run them. And then, do logs over an API. So let's do a little bit of a deep dive on what steps is going to look like. So I'm going to call this steps/Taskonaut because we're pulling from both of these. So GitLab is going to produce a proto payload. So now, instead of having just a big job build thing, we're going to have a steps proto payload. And it's proto just because it makes it easier to pass through. It makes it easier to version, generate clients to access it in a consistent way, all the benefits of proto. This is one of the ways in which the steps approach and the Taskonaut approach differ is steps assumes that you sort of get this proto payload from GitLab directly at the outset. Taskonaut has sort of an executor API where you give it the stuff from GitLab and you get those steps back. So whether or not we have production of steps as a pluggable interface is one difference. So my understanding is we're going to kind of start with the steps approach where we get the proto payload from GitLab itself. And then Runner actually uses the executor to produce an environment, again, same as before. So it gets this executor back. But instead of doing this build executor combination, it actually injects, that proto payload unaltered into step runner. So step runner is that agent which lives inside the environment. This gRPC would be run. So you actually run these steps and it's the whole job, right? The whole job, not just like one step at a time. And it's agnostic to like what those steps are doing. So this implies that there's some compilation that happens over here, right? That sort of takes, GitLab CI and produces steps. And that's a whole big chunk of work. And the steps that it's going to produce are going to include those built-in steps. Like one of the steps is going to implement downloading the source code, pulling down the archives for the cache, pulling down the artifacts. Those are all going to be exploded into like individual steps so that Task Runner doesn't need to know about what, like what specific thing is happening. And that also gives us a little bit more latitude because you can take things like GitHub Actions and you can compile them to steps too. Because GitHub Actions actually has a much more modular sort of like step-like approach where each one of these things, like cloning the source, is its own step. So compilation here is its own problem space. And this is what Camille is going to focus on. And my goal is to focus on this pipeline, the whole the low-level steps, the runner of the steps, and how we get it into the environment. So we're sort of splitting some of this work between me and Camille. And then, of course, getting logs back out is going to be a follow API. And I was proposing the exact same API as what Taskonaut provided. So this is one of the things that's just straight up lifted from Taskonaut. Now, one of the nice things about this is this executor, like, it gives you the environment, it injects the thing in, and what you get back is like pretty much the same API. So regardless of what executor you're using, you just call follow, right? And the executor is responsible for getting you connected to that gRPC service. And if the connection drops, the executor gets you connected again to the gRPC service, and you just kind of pick up where you left off. And we can design these APIs so that you can provide like a byte offset for how much you've already received, and you could pick up the logs where you left off. And it allows for other control signals to be passed explicitly, like, hey, I have a big upload, give me more URLs. Or here, please cancel this job. Or, tell me how far you are in your progress. Or I don't know, whatever we can dream up that you would put in a gRPC service, we can just sort of model it this way, all multiplexed through that byte stream, bidirectional byte stream. Yeah, so the idea of the jobs being executed in a consistent way also means that we don't need to couple the way that the jobs are executed to the executor enumeration. So some of the things that make Kubernetes executor very unique don't need to actually be as unique. We can reduce a lot of the code. It's like a lot of the build code here goes away, right? And a lot of the executor specific code goes away. And that's why I wanted to talk more about executor reduction. So in this new model, there's not that many executors that we actually need, right? We need the instance executor. We need the Docker executor, the Kubernetes executor, and the custom executor. And each one of these executors needs to run in an environment. So with these orthogonal aspects, scaling is now handled by Fleeting. And we have, AWS, GCP, we have Azure, we have a static plugin, which gives you like points to one or more, just like pre-listed instances, or whatever cloud environment you want to provide. Like this is meant to be like just access to capacity. Then VM isolation, I mentioned this already, but it's provided by nesting. And this gives us an API to a couple curated VM management layers that we support. We don't open this up as much because investing in VM management is expensive. I mean, it takes a lot of time in development. Job injection is now the role of the executor, which is much reduced. And now job execution is largely the role of the step runner. And this is the in environment agent. So these aspects are being separated. So the executor reduction blueprint kind of goes through this a little bit, explaining why it is that we don't need an SSH, a shell, all of these other ones. It's really more about now how you get this payload in there. And so, for example, the instance executor, right? It uses SSH and then connects to, right now, it actually just runs a command, but what it will do with steps is it will connect to a Docker and connect to a gRPC service running on a socket. This is actually exactly the same way nesting works. Nesting starts up as an agent inside of the VM, serves on a local socket. So auth access is controlled by SSH mechanisms, right? So once you get into the machine, you just hook up to that socket and use that as a bridge to send bytes back and forth. And so the same will be done for, accessing the step runner. Docker will exec and connect to the gRPC. It'll use a bridge. So you'll tell whoever's managing the Docker container, usually the Docker API, right? You say, please run this command in this container. And so it'll run the command. And what the command does is command starts up, knows where the step runner socket is, connects to it, and then just acts as a bridge. So from the output of exec, you have a byte stream connecting to the service, and you can start making service calls. If it drops, you just exec it again. Like if it crashes, you exec it again and continue with your API calls. Kubernetes works the same way, except the exec goes through the API server, and the API server does the auth, and then it connects to the kubelet, which has a server, and then the kubelet will actually go into the container and do the exec. And you negotiate the HTTP post up to a bidirectional speedy streaming API. But under the hood, it's execing into a container in the same way. So that's why we don't really need all that many executors. The executor's role is much smaller. It provides something that we can treat the same way, this client connection to a client, etc. So that's how those three blueprints, Taskonaut, steps, and executor reduction are related. So let's talk about events. What do events have to do with this? This is a fourth blueprint. So the idea is, we would like to have, code that runs in response to things that happen. So like, you get a merge request, or, somebody, tags an issue or whatever. There's a bazillion things that happen. We want this to be a programmable, and we want GitLab to be a programmable environment. And there's a bunch of stuff that happens, and we want to be able to run code. You can do that already with webhooks, right? You can set up a webhook, point it at a service, start a service, catch the events that happen, do stuff, make an API call. The problem is this is, slow, because, you have to have this whole service call, events has to get processed. The webhook has to get processed asynchronously. It's not like wired really deeply, right? Because it's an external service. And you have the overhead of running a service. I mean, if you're just there and you just want to add a label to somebody's MR, you don't want to stand up a service to do that. Right? Like it's a lot of overhead. So really what we want to do is we want to provide a hosted environment to run untrusted code. So instead of you standing up a service, you just give it to me. And when this event runs, I'll just run this code for you. It's like serverless, right? And this is actually pretty much what Runner does already, right? Like you give it some code and stuff happens, and we look at your definition and we run your code for you. But the problem is Runner is kind of slow for this kind of a use case, because it has to clone your whole repo, has to pull your cache, etc. So what we really want to do is we want to remove the hard-coded steps. We want to only do the thing that the users asked for, like, make an API call to add this label. So with steps, once we have this low-level mechanism for producing, concrete steps into the runner system, you could just leave off the GitLab clone and all the other things that you don't want. And you can just give just a real small code snippet to run, or a reference to a code snippet. And it makes it much, much more lightweight. Additionally, So that's one of the reasons why steps is useful for events, is it trims some of the fat off the outside. And then there's also the issue of how to run it. So this is one of the places where steps is related to runner, but not really about anything I've talked about so far. When you run that, you want to run it in a trusted environment, or you want to run it in a sandboxed environment. And so like what kind of sandbox environment do we want to provide? A lot of what we have so far is around putting things in VMs, putting things in instances, and there's a lot of overhead to creating those environments. But we want to like process like hundreds of these per second, right? Like it needs to be lightweight. So for the purpose of events, Runner is looking into maybe doing something like hosting WebAssembly as a target. So maybe having a WebAssembly executor or something. And rather than, making environments remotely, it would just have like a huge capacity for, a bunch of WebAssembly VMs and just spin those up and run those WebAssemblies. And WebAssembly is very well sandboxed. For anybody that doesn't know what it is already, it's kind of like a successor to JavaScript, right? There's a lot of languages that compile to JavaScript. JavaScript's available everywhere. It's well sandboxed and trusted. WebAssembly is just kind of taking that idea a step further and saying, just give me bytecode and I'll run it. So we can, if a user is able to provide code, we can compile it into WebAssembly and run it in the runner itself. That requires making Runner quite a bit faster on multiple dimensions. In addition to dropping additional steps, we need to make the interactions between Runner and GitLab more efficient, so that we can process them quickly. So that's what I'm thinking about in the event space. It has some overlap with steps, but there's some additional like stuff there too. So yeah, thanks for watching. That's a very large like picture of stuff, but overall the goal is to start taking all the stuff that's been coupled inside of a runner, start teasing it apart into different orthogonal pieces that we can use, test, and recompose in different ways to produce stuff like GitHub action compatibility, more consistent execution to reduce the amount of code and to reduce the number of bugs. Make Runner manager itself stateless so that we can reconnect to jobs to improve reliability. Process events to make Runner capable of backing any kind of workflow that happens inside GitLab. All of these things are enabled by this general trend and desire to reduce the number of things that we have, pull them apart, put them behind interfaces, and recompose them. So yeah, thanks again for watching. I'll post some links to the actual blueprints in the description, and I hope that this was helpful in clarifying how some of these things are related. Bye.